In this video, we're going to be talking about linearly independent vectors. For a set of vectors to be linearly independent, you have to take the system AX is equal to 0, and then you have to prove that there are no possible x's or combination of x's that would be multiplied by A to give you the 0 vector. For a set of vectors to be linearly independent, this would be true only if x is the trivial solution where all the x is equal to 0. So basically what this is just saying is that you can't make a vector from the other vectors in the set. So for example, on the right-hand side, you have an image of the set of vectors v1, v2, v3, right? v3 is nothing like v1 or v2, which means you can't create a linear combination of v1 and v2 that would give you the vector v3. That's basically what linearly independent vectors mean. They don't like each other. They don't associate with each other. They don't want to be anything like each other. They pretty much hate each other. Now let's look at the theorems. For theorem A, the set v1, v2, all the way to vn is linearly independent if the following system, I'm not going to say all that, has no free variables. You don't want any free variables. They all have to be basic. And if there's only basic variables, then that means the only solution is the trivial solution, where you just set all of the x1, x2, all the way to xn equal to 0. You want that to be true for a set to be linearly independent. Now, for a set of vectors to be linearly dependent, there has to be a linear dependence relation among the vectors. This is just basically saying you can make a linear combination of the other vectors to make one vector. So if I look back at the example of v1, v2, v3, if you were able to create a linear combination of v1 and v2 to make v3, then the entire set is linearly dependent. Doesn't matter if there's only one linearly dependent vector in there. Another really easy way to tell if a set of vectors is linearly dependent is if there's like a 0 column vector. Let's think about it this way. Going back to the v1, v2, v3 we had, imagine if v3 was the 0 vector. If I wanted to make a linear combination of v1 and v2 to make v3, I could just set it all to 0, and that would technically be a linear combination, which would make v3 dependent. That's why having the 0 vector makes the entire set linearly dependent. Now the last two of these theorems have to do with pivots. If the number of vectors, the column vectors, is greater than the number of components, which is like x1, x2, so on, then there are not enough pivots to cover the entire matrix, which means there has to be a free variable. Because going back on the other videos, what is a pivot? A pivot is where the basic variable is. And if there are not enough pivots or basic variables to cover the entire matrix, then there has to be a free variable. There's nothing else. So therefore, if there are free variables, there have to be linearly dependent vectors, which would make the entire set linearly dependent. Now let's look at this first example. Determine if the set of vectors below are linearly independent. If possible, find a linear dependence relation among them. So here, what we're going to do is set up our equation AX is equal to 0, because that's how we check if a set of vectors is linearly independent. So then we combine v1, v2, v3 into one big matrix A. And then we add the 0 vector on the right-hand side. So now we can row reduce. The most obvious thing we can do first is multiply row 1 by a fourth, and then row 2 by a half, and it would give us this new matrix. Now we can start getting rid of anything below the diagonal pivots. So row 2, we're going to add negative row 1. And then in row 3, we're going to get rid of that 3 by multiplying row 1 by negative 3, because 3 plus negative 3 is 0. You know that. Anyway, this gives us this new matrix. And as you can see, row 3 is 8 times row 2. That's a linear dependence, so we can get rid of that row. And because there's a row that we were able to eliminate, aka a linear dependence, we automatically know that this set of vectors is not linearly independent. Now looking at the second example, we have a new set of vectors. It's already put it into a matrix for us. Fantastic. Now, we row reduce. And the first obvious thing we can do is multiply row 2 by a fourth. And after rewriting the matrix, we get this. Now we just get the pivots done. So to get rid of that 1 in row 2, we add negative row 1 to it, and it would give us this new matrix. Now, we need to get rid of the 5 in the third row. So we multiply R1 by negative 5 and add that to row 3, which gives us this new matrix. Now, what we can do is multiply row 2 by negative 4 and then add that to R3, because we want to get rid of that 4 under the second 1 in the main diagonal. Now this gives us this new matrix. Since we have all of the pivots set up, the matrix is now echelon form. You can stop. Now let's look at this finished matrix we have. We have 3 pivots along the main diagonal, and there are 3 rows and 3 columns. Since the number of rows and columns equal to each other, and there are no inconsistencies, no redundancies, no row eliminating, this entire vector set is linearly independent. That's what we want to see. So that means for the vectors v1, v2, v3 within this matrix A, you cannot have any other linear combination of the 3 to equal 0 other than if you had set x1, x2, and x3 to 0, aka the trivial solution. Now looking at this third example, it's asking us, does the span of A contain the vector B? Which is basically this equation, ax is equal to b. We want to know if that's true, or if an x exists that would give us b. Another way of asking this question is, does a linear combination of the vector columns in A to create B exist? Okay, so we set up our augmented matrix with A on the left, B on the right-hand side. This time they give us B, 0, 8, 7. So we can start row reducing. And the first thing we notice is that we can multiply the first row by a fourth and the second row by a half to make it simple for us. So that gives us this new matrix. Now this is just a personal preference, but I don't like zeros in the pivot positions. So what I did is I just moved row 2 and row 1. I just swapped their positions. That gives us this new matrix, and now we can get rid of the entries below the pivots. So to get rid of the 1 in the second row, we add row 2 plus negative row 1, which gives us this matrix. Then we need to get rid of the 2 in the third row. So we add R3 plus negative 2 times R1. Okay, now that we have the first pivot set up, we need to get rid of the 1 under the second pivot column. So, as you can see, we can multiply row 2 by half again to simplify things. Now, after that, we add negative row 2 to row 3, and this gives us this new matrix. Now, notice that there is an inconsistency in the third row. That's not good. If the system has any inconsistencies whatsoever, B is not within the span of A, which also means there's no linear combination that exists within the vectors A that can give you B, because the whole system is inconsistent.